Good morning, everyone. All right, we're ready to get started. Today we are going to finish up the line integral section. We may touch into section 16.3 at least to start, because it ties in very nicely with this material. But just to summarize what chapter 16 is all about, it's about introduction to vector fields. So these are functions that have points as input or vectors as input and returns vectors as outputs. And we are doing the calculus of vector fields. In particular, we're focusing on integration problems related to vector fields. So our motivating example that we worked on last day was this example of finding the work done by a force field on moving an object along some path. And just to summarize what we've done here, so maybe I'll put a little summary here. The idea was we've got this particle that's moving along a path, and there's a force that's acting on it at every point as it moves along the path. And so this force acting on a point that's moving over a distance, there's work involved of that force field on the point. And so the work is just the product of the force applied times the distance that the particle has traveled through as that force was applied. The problem is the force is varying. So this formula, work equals force times distance, that's a formula for constant force over the distance that the particle has traveled. And also one other thing about this, work equals force times distance, is that's the force applied in the direction of motion. So what we did here with our diagram was we just broke it up into little chunks, and we said, okay, to get the total work, all we have to do is integrate over all of these tiny little work elements, where one of these dW's is just the amount of work done in moving the particle over a tiny little segment of its path. And when we move it over a tiny little segment of its path, we can assume that the force is constant over that little segment. And so if we assume that the force is constant over that little segment, then we can work out what the little dW is. It's just the constant force applied over the distance traveled. And that's what we ended up working out in this part here. We said, well, the little work element that's done is just the force in the direction of motion times the distance it's traveled. So the force in the direction of motion was F, the magnitude of F times cosine of theta. So that was the force in the direction of motion, and then times the little change in position. So that's the ds. And then we just unpacked what those things are, and it ended up being that dW was a dot product. So it was a dot product of the force at a given point on the curve times the direction vector at that point on the curve dt. And so that's, in summary, what we've essentially done here. So that one line really summarizes all of that stuff that I've done in green. Total work is the integral over all the work elements, and a little work element is just found by looking at a little tiny segment of the curve and figuring out what the work was on that little segment. And that is just the force in the direction of motion times the distance traveled in that direction. So that gave rise to this integral, which I've highlighted at the bottom, so I'll just leave that one visible. So summing over all the works gave rise to that integral, which we've written down. And this is an example of one of the types of integrals we will be studying in this section. This is an integral of a vector field along a space curve, or what we say is an integral of a vector field with respect to a space curve. And we'll see that with respect to a space curve, why we can write it down like that in a second. Another type of integral that we'll be interested in is an integral of a scalar field, but along a curve as well. In this case, it'll be a scalar field with respect to arc length. So we have essentially gone, if you want to think of it this way, we've gone backwards from what we did in chapter 15. In chapter 15, we looked at double and triple integrals, essentially extending the ideas from Calculus 2 to regions in the plane and regions in space. And so those were integration over areas or integration over volumes. Now we're going to come back to this idea of integrating along a line. And so in Calculus 2, we were just integrating along one of the axes, either the x-axis or the y-axis. But now we're going to integrate along curves in higher dimensional space. And these are called line integrals. So a line integral, much more appropriately called a curve integral or a path integral, because these curves we're integrating over aren't going to be straight lines. They can be any parametrized curve, but this is the traditional name that's given to them, line integral, as opposed to an area or a volume integral. And so that's the name we'll be using. But if you want to substitute curve integral or path integral in place of that, just to conjure up in your mind that these are really just integration or integrals over curves, then you're free to do that. So we're going to look at each of these two kinds of line integrals: an integration of a scalar field with respect to arc length and an integration of a vector field with respect to a space curve. And that's our topic in this section, is just looking at some examples of each of these and how they can arise. So what we'll do is we'll start off with the first one, integration of a scalar field. So when we say the integral of a scalar field, we just mean that there's some little function f of x, y, possibly z. It could be a couple of different variables, 2 variables, 3 variables. But the idea is we've got a function, multiple inputs, a single output. That's as opposed to a vector field, which has multiple inputs and multiple outputs. So when you see the word scalar field, just think of a function, little f. And so the line integral of a scalar field is given by this definition in the box. So we've got a curve C, which we're assuming to be smooth, and that means that we got its derivatives existing because we're going to need those. Then the line integral of f along the curve C is given by this notation. It's the integral with a sub c. This is analogous to our integral over regions in the plane, or our integration over volumes in space, where we use letters to denote those regions like T or E or R or D. Here we're just saying we're integrating over this curve C. The function we're integrating is f of x, y, and we are integrating it with respect to arc length ds. And then, as I mentioned last day, right at the very top of the page, we had this ds dt is equal to the magnitude of r prime of t, and I said that was going to be used pretty much again and again and again in this section. We used it once already here to go from ds to the magnitude of r prime of t dt. That's where we used it once. So what is our arc length element? It's the magnitude of our tangent vector times dt. We're going to be using that again here, where we unpack ds as this whole expression here, which is just the magnitude of r prime of t, that thing unpacked as the square root of the sum of its components squared, dt. So that's just an unpacking of that first integral. So what I want to justify to you is, why would we consider such an integral? This integral of f of x, y, ds. Why would such a thing even come up? And I'll give you one example, and then we'll see as we do some further examples how it would come up in other contexts. But this is really the idea. Maybe I'll switch over to a demo here. Oh, I lost my demo. I'm gonna have to add a new one. Just give me 1 second. For some reason, it didn't like the browser window that I was opening, so I'm just adding a new source right now. Just take me a second because I can't seem to find there it is. There's my source. Okay. All right, there we go. Sorry about that. So here's the idea. We've got some function. This is our f of x, y. And in this case, our function is f of x, y equals x. And what we'd like to do is we'd like to consider some curve in the plane. So I've got that curve drawn there in green. This is actually an example we'll do in a little bit. But I've got some curve in the plane. And so then what I can do is I can see, okay, what are the images of this curve in the plane, those points, up on the surface? So if I think of my function f of x, y as just taking points on the green curve as inputs, what are the outputs? It's that red stuff that I've drawn up on the plane itself. So those are the outputs of the points on the green region in the xy plane. So now I've got inputs into my function on the green curve. I've got outputs of my function little f, which are the points on the red curve. And what I can do is I can fill in the space in between them, kind of like a curtain. And so if I fill in the space between them, there's the space between sort of that first curve and the stuff on top, and then the other part of the curve because it has a little kink in it. And so there's the filled in stuff in between. And I could ask, what is the area of this curtain? What is the area of the blue region? And if we think about how we would do this, well, we'd like to integrate along the green curve. And I'd like to sample the height at each point along the green curve to get the height of the curtain. I'd like to integrate then the function values along the green curve. But when I do this integral, I want to know, okay, I've sliced it up into a bunch of little bits. If I think about it as an area problem, then I'm going to need to know what is the width of a little bit. And a width of a little bit is given by the length of the green curve that I've sampled along. And so that's essentially the arc length of the green curve. So what I'm doing is I'm integrating my function against the arc length of the green curve. So we'll get another view of that. But that's basically the idea of what we've got in order to come up with this integral. So I'm going to look at this picture down below, and I'm just going to think that I've got a curve in the plane. This is what I want to integrate along. I've got my values of my function at points on the curve in the plane. That gives me this upper curve. And then I've got that space trapped between those two curves, that shaded region. And that's what I want to find the area of. So the way we do it is just like we do all problems for integral calculus to set up an integral, to initiate these things, is we chop it up into a bunch of little bits, do a small area on each of the little bits, sum them all up, let the thickness go to 0, and turn it into an integral. So that's our main process. So what we're going to do is we're going to chop our curve up into little bits. So I'll look at my curve now. I'm going to look at just this little tiny portion there. So there's my little tiny portion of my curve. And if I know that it's what its width is, and its width I will call, or it's the length of the segment, is what we'll call delta S. It's a small change in the arc length. Then that's going to give rise to something in the other picture that kind of looks like this. Now we're over some delta S. We're going to sample our function there, and we're going to be essentially, and I'll zoom in a little bit, we're essentially trying to work out the area of this portion of the curtain. We've got P I minus 1, that's our point there. We've got our other point, P I, and this Pi minus 1 is essentially given by xi minus 1, yi minus 1. And this point pi is xi, yi. If I want to find the area of that region, then I imagine it's just really, really thin. In fact, you can see sort of vertical lines drawn all the way along. The idea is right now I'm spanning 3 of these sort of vertical lines. So I'm taking 3 of these sort of panels, but the idea is we take it thinner and thinner and thinner and thinner. And the thinner we take it, the better the approximation is. So what I'm going to do is I'm just going to pick a sample point, go up, sample the height value there, and then just cap it off. And so I will form a surface that has constant height along the surface, and its base, if I flatten it out, it's basically a rectangle whose base is delta S and whose height is going to be f of xi star yi star, the function value at the sample point. So now I've got a rectangle with height f of xi star yi star and whose base is delta S. So that gives us the fact that the area of a small, we'll call it slice of the region is the height f of xi star yi star times the base, which is delta S. And so our total area of what I've called the curtain. So thinking of just a curtain is just, we got fabric hanging from this bent rod, then maybe this red rod, we've got fabric hanging from it, and it just sort of flows down until it sits above this green curve down below. And we're just trying to find the area of the fabric between these 2 rods. The total area of this curtain is given by the sum over all of these area pieces, these areas of these slices. But then when we sum over all of them and take the limit as the thickness goes to 0, then what we get is our integral, the integral of f xy ds. And so that's our integral of our scalar function with respect to arc length. And so that's where this integral comes up. And then, of course, from above, we can replace ds with the magnitude of r prime of t dt. But what we've done is we've just justified where this formula is coming from, why we are even considering it. It's going to be the area, so it's extending the stuff we did in calculus 2, but now for functions in whose surfaces can be drawn in 3 dimensions or functions of 2 variables. And we're integrating over curves in the plane. And so we're integrating against the arc length. So you can think of it as just the area of the region between them. Another example that we will do is, we'll do this in a moment, is we could think of this, this rod, this green rod that I've drawn in the plane. That could be some rod that I know the linear density function of. The linear density function could be f of xy. So that's the density at any point xy along that green rod. And so how would I get the mass? Well, mass is density times length. So if I chop it up into a bunch of little bits, then the length of a little bit is ds. The f of xy times ds is the mass of that little bit. And so integrating over all of the masses gives me the total mass of the object. And therefore, this integral could come up when we're looking at the mass of a linear object with varying density and other contexts as well. So these integrals of scalar functions with respect to arc length will come up in other contexts. Let's have a look at an example of actually computing one of these things. So we want to evaluate the integral of x with respect to arc length ds over the curve C, where C is the arc of the parabola, y equals x squared from 1, 1 to 3, 9, followed by a line segment between those 2 points. So let's get a feel for what this looks like. So we've got our parabola going to look like this. Particular, I'm interested in it from the point 1, 1 all the way up to 3 and 9. So there's our part of the parabola. Let's call that curve C1. And then from 3, 9 to 4, 7, it's going to be a straight line. So this is 4, maybe we'll call that height 7 there. And so we got this straight line. So there's 4, 7, there's 3, 9, and there's 1, 1. And then I've got that other curve, which I'll call C2. So together, C1 and C2 make up the whole curve C. And what we'd like to do is integrate the function. Our function in this case, f of x, y, is just equal to x, because we can see that from the integral. The integrand is just x. And so we want to integrate that function along this curve. And we'll do it just curve by curve. C1, and then we'll integrate along C2. And so the integral along the whole curve is just the sum of those two integrals. So for C1, what we have to do is come up with a parametrization of it. So again, what we're doing is just doing this integral here. We're going to integrate along the curve, the function with respect to arc length. So I need to know a parametrization so that I can substitute x and y in terms of the parametrization, and I can substitute ds for the expression in terms of the parametrization, which was magnitude of r prime of t dt. So I need to know a parametrization for the curve. So what is our parametrization going to be? Maybe I'll call it r1 of t. So this is going to be a parabola. Y is equal to x squared. So if I took t as my parameter, so x is t, y has to be t squared in order to give us a parabola. So there's my parametrization of the curve. It's t squared. And t is going to range over the values from, well, t is our x value, so it goes from 1 to 3. So there's our parametrization of curve C1 with our starting and ending points. That tells us then that x is t, y is t squared. So dx dt is 1, dy dt is 2t. And those are the ingredients I need in order to work out the integral. The integral we want to evaluate is the integral over C1 of x ds. And so now we just put everything in terms of t. It's essentially a substitution is what we're doing here. We're substituting x for its expression in terms of t, y for its expression in terms of t, and ds for its expression in terms of t. And our limits of integration go from 1 to 3. So x is t, ds is the derivative of x with respect to t squared, so that's 1 squared, plus the derivative of y with respect to t squared, that's 2t all squared, dt. So this is the integral from 1 to 3 of t times the square root of 1 plus 4t squared dt. And so this is the integral we would need to work out. So the first little bit is just setting it up. Taking our integral of our scalar function with respect to arc length and then writing it as an integral of a single variable, in this case, the value of the parameter or the variable, which is the parameter t. So now we're into an integral that we can compute. So I'll spare the details of actually doing the calculation of this integral. We get a value of 1/12 37 to the 3/2 minus 5 to the 3/2. So that's our first curve, C1. Then we've got a second curve that we still have to work out, the integral along. So what is C2? We're going to come up with its parametrization. So it's a line. It's a line that goes from 3, 9 to 4, 7. So I can write its parameterization of 3, 9 plus t times the vector in the direction of the line. So I can get the vector in the direction of the line by just taking the tip minus tail. So that vector there is given by 4 minus 3, which is 1, 7 minus 9, which is -2. And so there's our direction vector for our line, 1, -2. And in order to get that line segment, t ranges over the values from 0 to 1. And so that tells me then that x is equal to 3 plus t, y is equal to 9 minus 2t, dx dt is 1, dy dt is -2. And so I've got all the ingredients now in order to do our integral. So our integral, I'll just put it off to the side here, our integral c2 x ds is given by the integral from 0 to 1. And then x is 3 plus t. ds is the square root of the x derivative squared, which is 1 squared, plus the y derivative squared, which is -2 squared dt. And so that's now under the square root sign, that's all a constant, so that can come out. So we're basically just integrating a linear function. And so again, I'll spare the details of the integral, and what we get is 7 root 5 over 2 for our final result. And so that means, so therefore, the integral that we wanted was the integral over the whole curve C of x ds. And that's the integral over the first curve plus the integral over the second curve, which is the sum of these two values, 1/12, 37 to the 3/2 minus 5 to the 3/2, plus 7 root 5 over 2. And so there's our final result. Okay, now what can very easily happen here is we do all this calculation and we lose sight of what we actually calculated. What was this thing we actually calculated? So let's go back to our visual. What we actually calculated, so I'll start with turning a few things off, was we have, maybe I'll even turn this curve off. So we've got this function, f of xy equals x. So basically z is equal to x is our plane here. And then what we did was we took a curve in the xy plane. That's the portion of the parabola followed by the line segment, C1 followed by C2. And we worked out the integral of this scalar function with respect to arc length along this curve. So in other words, we found the area of the region between the green curve and the red curve. And we did that in two parts. We first found the area of the region above the parabola, which was that blue surface there. And then we found the area of the region between those two line segments. And we added them together to get the full area of that surface. So that's what our calculation was. So what this allows us to do now, instead of just integrating like in Calculus 2, find the area of the region between these two curves, in Calculus 2, we would integrate along like the x-axis between two function values. Now we've extended this. We can say, find the area of the region between these two curves, where these two curves can be parametrized curves in space. So I can find the area of the region between the green curve and the red curve. So we've done a nice generalization of concepts from Calculus 2. All right. Now there's no reason we need to stop in 2 dimensions for our integration along space curves with respect to arc length. We can carry these same ideas up into 3D. In this case, we just need to know a parameterization for our space curve in 3D. So that's our curve C, given there as x of t, y of t, z of t. And if f is a function of 3 variables and is continuous in some region containing that curve C, then the line integral is just the same as we defined above. It's the integral along the curve of our function with respect to arc length. And ds, just like it did before, the ds part, the arc length differential, unpacks to the magnitude of r prime of t dt. And so that's just written down in the next line, a nice sort of more compact form of this integral. And so this is the one we'd like to keep in mind because it's a little bit shorter to write, but it has all the information we need. We're going to integrate a function of t with respect to t. Our function of t is going to be f with the parameterization substituted in for x, y, and z, and then the magnitude of r prime of t dt are the other parts that we need. So let's go ahead and do an example. Now, what I want to do with this example is to just illustrate that the integral that we have up above, we can encounter it on our own. So you may encounter questions in the textbook that just say find this or calculate that, and there's no integral given, right? There's no integral given in this question. So what we have to do is figure out what the integral is, and so we do it just from basic principles. Find the mass of the helix if the density of a point is given by rho of x, y, z equals x squared plus y squared plus z squared. So the way we're going to do this is we just think, okay, what is mass? Mass is equal to density times length. In this case, it's a linear density, so it's times length. If it was a planar density, so if it was a region in 2 dimensions, then we'd be multiplying density times area. Or if it was a volume, a 3-dimensional object, and we had the density at all points in that object, then mass would be density times the volume of the object. In this case, it's a helix, so it's just a curve. So it's an object that's 1 dimension. The mass is the density times length. The problem is density is varying. So what we do is we work out what is our total mass that we want. So this is the formula we keep in mind for constant density. And we say, okay, but our density isn't constant here. So what do we do then? Well, if our density isn't constant, then the way we compute the mass is by integrating over all the little mass elements. We just chop our object up into a bunch of little pieces, find the mass of each little piece, and sum them all up. And then look at what happens in the limit as the length of the pieces go to 0, and that turns into an integral. What is our mass element? What is the mass of a tiny little piece? The mass of a tiny little piece is going to be the density of some point along that tiny little piece, but because the piece is so tiny, we can assume the density is constant. So it's density times the length of the little piece you have, and that piece would be of length ds, this little tiny arc length. And so now you can see we've just, through sort of intuition and just using the idea that mass is density times length, and our density is varying in this case, we've come up with the integral that we just introduced in the previous box as known as the line integral of a scalar function with respect to arc length. So we just came up with that. And so in order to evaluate that, what we're going to need to do is we're going to need to use our parameterization. And so we're going to go the integral from 0 to 2 pi. Rho of x, y, z is going to be rho of cos t, sine t, t. Basically, now we're just doing a substitution for everything in terms of t. What is ds? ds is the square root of the derivative squared. So derivative of x squared, that's negative sine t squared, plus the derivative of the y parameterization squared, so that's cos t squared, plus the derivative of z with respect to t, which is 1 all squared dt. And so there's our integral we need to compute. The row function is x squared plus y squared plus z squared, so we can work that out. That's cos squared t plus sine squared t plus t squared. And then under the square root sign, we have a sine squared t plus cos squared t plus 1 dt. And sine squared plus cos squared is 1. So we get some nice simplifications in both of those expressions. And we get the integral from 0 to 2 pi of 1 plus t squared. And then the other part becomes a root 2. So I'll put that out front, root 2 dt. And so that ends up being our expression for our mass. And so we can go ahead and work it out, but I'll just spare the details because we're more interested in just setting these things up. So this becomes a 2 root 2 over 3 pi times 3 plus 4 pi squared. And it's just integrating a parabola at this point from 0 to 2 pi. All right, so and as with all the questions sort of in chapter 15 and 16, the idea is the new stuff is setting up these integrals. So we get the integral set up, and then the calculation, I'll probably mostly skimp on the calculation because in these cases it was just either a linear, it was integrating a polynomial, which isn't challenging, doesn't require us to use any special techniques from calculus 2. All right, so that was a 3-dimensional example of integrating a scalar function with respect to arc length. So in this context, it was density, and we wanted to find the mass of the rod. So essentially extending the ideas that we did in chapter 15 for planar lamina and volumes with varying densities. Now we've come back to this density of a 1-dimensional object and where it's varying along the curve. All right, so let's get into that other type of integral. This is that second type of integral that we introduced at the beginning. Line integral of a vector field now along a space curve.
So, Professor, can I ask a super quick question?
Yeah, go for it.
About the length that you just did in the example before. I also just joined, so
okay.
sorry.
Welcome.
Yeah. Thank you. Why is it 1 squared instead of t squared? Oh no, sorry. Yeah, I answered my own question.
Okay.
It's a partial derivative. All good. Thanks.
You got it exactly. Yeah. I can even jot that in here. So this was dx dt. That one was our dy dt. And then this one came down as our dz dt. Yeah, that was our magnitude of r prime of t that was coming up there.
Makes sense. Thank you.
You're welcome. All right. So now we're going to introduce the line integral of a vector field. So this is a definition. It's just, if you have a vector field, this is the definition of a line integral of that vector field along a curve C. There's a lot going on in this definition. We'll unpack it in just a second. But I do want to just remind you that we have already done this. This was our motivating example. We had a particle that was traveling along a curve through a force field, and we wanted to know what was the work done by the force field on that particle. So we only care about the force that's pointing in the direction of motion. So we only care about at this, at any given point, we zoom in on, there I've got a point there, maybe that blue dot. At that point, I have a force acting on that point, and that is the force given by that yellowy orange vector F. But I only care about the force in the direction of motion. And so that's where we get this F projected onto the tangent vector. And that's that sort of F cos, magnitude of F cos theta. In fact, it's coming about as a dot product of F dot R prime. So the projection essentially of F onto the tangent vector. And so that's what we're interested in. Only the part of the force that's in the direction of our tangent vector, in the direction of motion. And so that gives rise to this integral here. This is what we care about. The integral of our vector field evaluated at a point on our curve, dotted with the tangent vector to the curve. That gives us essentially our force in the direction of the motion. And then we integrate that with respect to t over the interval a to b. This previous one, that's just shorthand for it. This is just shorthand for it, where we're using dr as a shorthand notation. So this is d of a vector. This is something we just don't have this introduced. D vector, differential of a vector. That's not something we've introduced. It's just shorthand. It's just shorthand for r prime dt. That's all it is. And so that's just a nice shorthand way. F dot dr just means it's F dot r prime dt. So that's just a shorthand. The right-hand side is also just another sort of shorthand way to write this integral. The idea with this part that's happening on the right, or this other way of writing it using the unit tangent vector, is as follows. The unit tangent vector is given as r prime over the magnitude of r prime, but the magnitude of r prime is also written as ds dt. Again, that thing that I said at the very beginning, where I wrote down up by the title, I'll zoom back, right up by the title there at the very top right of the page, I said we're going to be using ds dt equals the magnitude of r prime of t over and over and over again. And we used it here. So we've got this expression, and then I just split up the ds dt and rewrite it in the following way. I move the ds over, and I keep the dt with the r prime. And then it just says, oh, okay, wherever I see an r prime dt, I could replace it with a unit tangent vector ds. And that's all that's happened here. It's just this part got replaced with this part. So those are all just shorthand notations for that integral in the middle, in that green box. That's the integral we're interested in. That's how we're going to compute it. When we read off an integral like that, what we essentially have is our vector field, which is given by these three scalar functions, p, q, and r. We've got our curve, which is given by that parameterization, r of t. And so if I want to work out the integral in that green box, well, what I'm really interested in is f dot r prime of t dt. So that's the thing I'm really interested in. That's my integrand. Right? That's my integrand up here. And so what is a way I could write this integrand? Well, I could write it as p times dx dt plus q dy dt. I'm just taking the dot product of f and r prime in this case, r dz dt. And then I've got that dt hanging on the outside. So this is just using the fact that f is given by these three scalar functions. And so I can do this integral, or sorry, I can rewrite the integrand in this way. And then just as a bit of shorthand, I can scale through the dt to get rid of the one on the bottom. So I could write my integrand of p dx, q dy, and then r dz. And so that's all that's been written here in the line above, is just we could write our integral in this way. And this is how often integrals will be presented to us. We just have to read from that expression what is our vector field. It's given by functions p, q, and r. And then whatever our parameterization c is, that allows us to get our dx, dy, dz, because dx would be just the derivative of the x function with respect to t, dy would be, and so on. There's our differentials. One of the nice things about sort of writing it in this way is it starts to come back to this idea of, oh, an integral of a vector field seems to be just the integral of three scalar functions. So these look like scalar integrals, but they're no longer with respect to arc length, they're with respect to the variables. So there's some nice tie-in with maybe the scalar functions, but we don't have to worry about that. If there's any takeaway from all of this, it's that this integral right here is the one we're interested in, and that's how we're going to evaluate it. So let's do some examples of these integrals of vector fields over curves. So we'll grab our ingredients. We've got our vector field we're interested in, and we've got our curve that we are interested in integrating over. So the ingredients, what I need is I'm going to need to know what r prime of t is, because I'm going to need to dot that with f at r of t. So what is r prime of t? That's 1, 2t, 3t squared. Then I'm going to need to know what f at r of t is. So f is the first component is x times y. And so if I plug in r into that, maybe I'll just make a note that that's x, this is y, and that's z in terms of being functions of t. So x times y is t cubed. Y times z is t to the fifth. And x times z is t to the fourth. And so the integral we want to compute, which is the integral over our curve of f dot dr. So that's just our shorthand for the integral we want to compute. When we unpack it, it's the integral from 0 to 1 of f r of t dot r prime of t dt. So again, that's what I said by this is the integral we really are interested in, and that's how we're going to compute it. So it's the integral from 0 to 1. F of r of t is t cubed, t fifth, t to the fourth, dot. R prime of t is 1, 2t, 3t squared, dt. And so there we go. We set up our integral, and that's the integral we want to compute. This is just a polynomial. It's just a polynomial. When I take the dot product of those two, I'm just going to get a polynomial of degree 6 at most degree 6. So maybe we'll just write it out. But at this point, we should have some foresight to say, oh, okay, when I dot those things, I get a function of t. It's a polynomial. Okay, at this point, the integral is going to be just a pretty straightforward integral. But let's go ahead and work out the dot product. So I got a t cubed, and then I get a plus a 2t to the 6 plus a 3t to the 6 dt, or I can write it as the integral from 0 to 1, t cubed plus 5t to the 6 dt. So that's the integral I want to work out. And it's probably easier for me to just work it out than it is to write the dot, dot, dot for you, because we are integrating from 0 to 1 of this polynomial. All that's going to survive are the coefficients. And so we get a 1/4 plus a 5/7 in this case. And so that gives us a common denominator of 28. And so I get a 7 plus 20 or a 27/28 as our result. All right, so that's it for this particular example. The last example, I'll just scroll up. The last example just has us do the same calculation, but in this case, we're going to do it over two different curves. So the first curve we do it over is over a curve C1, then we're going to do it over a curve C2. And so that means we're going to come up with parameterizations of C1 and C2 and then just do the integral. From the way the integral is presented, it's saying, hey, evaluate this integral. What we'll have to get from that is, that's just written in one of these shorthand ways, and that allows us to see the vector field so that they don't have to say, or we don't have to write it as, here's a vector field, now determine the integral. We can just write it as, here's the integral. So we're going to read from that what the vector field is. It's y squared comma x. So that's the vector field we're interested in. And so we just need to parameterize those two different curves and work out the two different integrals. I've done this already in the video, so I will leave it to you to see video for details. And I've even made a hint at the end of the video as to what's coming next, and I'll say that again here. What it turns out is that you get two different values. You get a value for the integral along the C1 curve, but then you do the same thing along the C2 curve, you get a different value. And that might be expected. I've just done two different integrals, one along one curve, one along another curve. What's going to be important for us are those vector fields for which it doesn't matter which curve you pick. As long as you start at one point and you end at another point, the integral is independent of how you go from one point to the other point. Those are going to be important kinds of integrals, and they only happen for certain kinds of vector fields, namely the conservative vector fields. So those are the vector fields that are gradients of potential functions, gradients of scalar functions. In this case, we get two different values, so that's just an indication that f is not a conservative vector field. I can't write it as a gradient of a potential function. So this is a bit of foreshadowing into what we're looking at in the next two sections, section 16.3 and 16.4. Conservative vector fields will come up, and we're interested in generalizing the fundamental theorem of calculus, computing integrals by analyzing antiderivatives. And this is going to be where conservative vector fields are very important, because they're the vector fields that essentially have an antiderivative to work with. All right, so I'll leave it there for today.